and welcome to Programming C course. In the last class I mentioned symbolic constant. Today let's see what is a symbolic constant. A symbolic constant is a name that substitutes for a numeric constant or a character constant or a string constant. It is just a name written in uppercase letters that substitutes any numeric constant, that is digits, a character constant, that is single character constants, or a string constant, that is an array of characters. Symbolic constant is usually defined at the beginning of a program. The symbolic constant may then appear later in the program in place of the numeric constant, character constant, or string constant that the symbolic constant represents. A symbolic constant is defined by writing has defined. There should not be any space between has and define. Then the symbolic constant name. Then the text which the symbolic constant will represent. Normally, symbolic constant is typically written in uppercase letters. Here, text represents the sequence of characters that is associated with the symbolic constant. Note that text does not end with a semicolon, since a symbolic constant definition is not a true C statement. Moreover, if text were to end with a semicolon, this semicolon would be treated as though it were a part of the numeric constant, character constant, or string constant. For example, has defined text rate 0.23. This statement is defining a symbolic constant called text rate, and it represents the numeric constant 0.23. Here, we don't put a semicolon at the end of this statement because defined statement is not a true C statement. If we put a semicolon at the end of 0.23, then that semicolon will be treated as a part of 0.23. Now, instead of using the value 0.23 inside our program, we can just use text rate to represent the value 0.23, which makes it more understandable about what 0.23 is. If we use 0.23, then we might think of 0.23 to represent just another numeric constant, not the text rate. So, to increase the understandability of the program, we can use text rate in place of 0.23 wherever 0.23 is required. The next statement is has defined pi 3.141593. Here the symbolic constant is pi written in uppercase letters, and the value it represents is 3.141593. So instead of using this long numeric value 3.141593 inside our program again and again, we can just use the symbolic constant pi. The next statement is has defined true 1. Here the symbolic constant is true in uppercase letter, and the value it represents is 1, which is a numeric constant. The next statement is has defined false 0. Similarly, here the symbolic constant is false and the value it represents is 0, which is a numeric constant. The next statement is has defined friend inside double quote Susan. Here the symbolic constant is friend written in uppercase letters, and the value it represents is the string constant Susan. When a program is compiled, its occurrence of a symbolic constant is replaced by its corresponding value. So, after writing the program, when we compile the program, wherever a symbolic constant exists, it will all be replaced by the corresponding value it represents. Thus, the statement area equal to pi multiplied by radius, again multiplied by radius, will become area equal to 3.141593 multiplied by radius, again multiplied by radius, replacing the symbolic constant pi by the value it represents 3.141593. The substitution of text for a symbolic constant will be carried out anywhere beyond a defined statement except within a string. Thus, any text enclosed by double quotation marks will be unaffected by this substitution process. For example, consider the following three statements. The first statement defines the symbolic constant representing the numeric constant 6.023 exponent to 3. The second statement declares as well as defines a variable c which is of floating point data type. The third statement prints whatever inside a double quotation mark, that is constant equal to %f %f is just a placeholder. It won't be printed on the monitor. In place of this, the value of the variable c will be printed. Here, the constant written in uppercase letters inside a double quotation mark will not be replaced by the value 6.023 exponent to 3 by the compiler, because the constant inside a double quotation mark is not a symbolic constant, it is a string constant. Therefore, the above printf statement will be unaffected by the symbolic constant definition during the compilation process, since the term within double quotation mark constant equal to %f is a string constant, not a symbolic constant. However, instead of the above printf statement, if it were printf within parenthesis double quotation mark constant equal to %f comma constant, then this printf statement would become printf within parenthesis within double quotation mark constant equal to %f comma 6.023 exponent to 3 during the compilation process, because the constant written in uppercase letter outside the double quotation mark will be replaced by the value 6.023 exponent to 3 because it is a symbolic constant, and the constant inside the double quotation mark will remain as such because it is a string constant, not a symbolic constant. Now let's see the advantages of using symbolic constants in a program. Symbolic constants increase the understandability of constants used in a program. They allow the constants to have more meaning. For example, if we use the symbolic constant pi instead of numeric constant 3.141593, it increases the understandability of the program, because when we use the numeric constant 3.141593 inside a long complicated program, it might just look like any other numeric constant, not the value of pi. So it is always recommended to use the symbolic constant pi instead of numeric constant 3.141593 to represent the value of pi. Symbolic constants improve the modifiability of the program. They allow the values to be easily changed in the header instead of changing all uses of the constants in the program. For example, inside a program, we might use the value of the pi 3.141593 several times. Now, if we want to modify this value, then we have to modify its occurrence of this numeric constant inside the program. But if we had used the symbolic constant pi, then we can just modify in the symbolic constant definition only. Symbolic constants save both space and time. Obviously, writing the symbolic constant pi instead of the numeric value 3.141593 again and again saves both space and time. Now let's see the rules of defining symbolic constants. The hash symbol must be the first character in the define statement. Blank space between the hash and the word define is not permitted. That is, there should not be any space between the symbol hash and the word define. Otherwise, the compiler will show error. Symbolic constant names are written in uppercase letters. To visually distinguish them from the normal variable names, which are usually written in lowercase letters, define statement must not end with a semicolon. Otherwise, the semicolon will be treated as part of the constant the symbolic constant represents. Now let's see some examples of invalid define statement to understand more how to define symbolic constants. The first statement, hash defined x is equal to 2.5, is an invalid define statement because is equal to sign is not allowed in a define statement. The second statement, hash space define max 10, is an invalid define statement because any space between the hash symbol and a defined word is not allowed. The third statement, hash defined and 25 semicolon, is an invalid define statement because semicolon at the end of the constant value that the symbolic constant represents is not allowed. The fourth statement, hash defined and 5, m10, is an invalid define statement because one define statement can define only one symbolic constant. The fifth statement, hash define array 11, is an invalid define statement because the defined word should be all in lowercase letters. The last statement, hash define price $100, is an invalid define statement because the dollar symbol or any special symbol is not permitted in a symbolic constant name. Remember all these rules so that you can define a symbolic constant properly. Now let us see the user defined data type def. Type def means type definition. Type def allows users to define an identifier that would represent an existing data type. The existing data types are char, int, float, and double. The user can give a new name to the existing data types by using the keyword typedef. Then the user-defined data type identifier can later be used to declare variables. Now, how to give a new name to an existing data type? It takes the general form typedef data type identifier semicolon, where data underscore type refers to an existing data type and identifier refers to the new name given to the existing data type. The existing data type may belong to any class of data type, including the user-defined ones. Remember that the new type is new only in name but not the data type, because typedef cannot create a new data type. Let's see an example. Typedef in units semicolon. Here the existing data type is the integer data type int, and we are giving a new name to this existing data type, and the new name is units. So instead of using the int keyword, we now can use the new name units to declare and define variables of int data type. The second statement, typedef float mark semicolon, defines a new name for the existing data type float, and the new name is marks. Now instead of using the keyword float, now we can use the new name marks to declare variables of floating point data type. So here the new name unit symbolizes the existing data type int, and the new name marks symbolizes the existing data type float. These names can then be used later to declare variables as follows: units batch1, batch2 semicolon. Here we are declaring the variables batch1 and batch2 to be of integer data type. Why? Because we have given a new name units to the existing data type int. Similarly, marks score1 square bracket 50, score2 square bracket 50 declares the arrays score1 and score2 to be of floating point data type arrays. Here, instead of using the existing data type name float, we are using the new name marks to declare the two arrays score1 and score2 to be of floating point data type arrays. The main advantage of typedef is that we can create meaningful data type names to improve the readability of the program. For example, whenever some variable is declared to represent marks of a student, we can use the new name marks in place of the existing data type name float to declare such variables to improve the understandability of the declared variable. Next, let's see the user-defined data type enum. Enum allows users to define an enumerated data type. Enumerated data type means listed data type. The user-defined enumerated data type identifier can later be used to declare variables that can have one of the values in the definition called enumeration constants. It is defined as follows: enum identifier within braces value1, value2, and so on, value n, followed by a semicolon. Here the identifier is a user-defined enumerated data type which can be used to declare variables that can have one of the values enclosed within the braces known as enumeration constants. After this definition, we can declare variables to be of this new type as below: enum identifier v1, v2, and so on, vn, followed by a semicolon. The enumerated variables v1, v2, and so on, vn, can only have one of the values value 1, value 2, and so on, value n. The assignments of the following types are valid. We can assign any of the values value 1 to value n to one of the variables v1 to vn. Now let's see an example of use of enum data type to understand it more. The first statement, enum space day space within braces Monday, Tuesday, and so on up to Sunday, followed by a semicolon, defines a new enumerated data type called day, which can take one of the enumeration constants Monday, Tuesday, and so on up to Sunday. The second statement, enum space day space week underscore start, week underscore end, followed by a semicolon, declares two variables week underscore start and week underscore end to be of enumerated data type day defined above, which can take the enumeration constants from Monday to Sunday. In the next two statements, we are assigning the enumeration constants Monday and Friday to the variables week_start and week_end respectively. Then the next statement, if within parentheses week_start is equal to Tuesday, checks whether the variable week_start is equal to Tuesday. If it is true, then the next statement will assign the enumeration constant Saturday to the variable week_end. Otherwise, if the week start is Monday, then the weekend will remain as Friday. The compiler automatically assigns integer digits beginning with 0 to all the enumerated constants. That is, the enumeration constant value 1 is assigned 0 and value 2 is assigned 1 and so on. However, the automatic assignments can be overridden by assigning values explicitly to the enumeration constants. For example, we can write enum space day space inside the braces Monday equal to 1, comma, Tuesday, comma, and so on after Sunday followed by a semicolon. Now the enumeration constant Monday will represent the value 1, Tuesday the value 2, and so on, and Sunday will represent the value 7. In the earlier example, the enumeration constants Monday to Sunday will represent values starting from 0, that is, Monday will represent 0, Tuesday will represent 1, and so on, and Sunday will represent 6. These are the automatic values. However, we can change these automatic values by assigning specific values inside the braces to the enumeration constants. Here the constant Monday is assigned the value 1. The remaining constants are assigned values that increase successively by 1. They don't have to be assigned separately. The definition and declaration of enumerated variables can be combined in one statement. For example, enum space day space within braces Monday, comma, Tuesday, comma, and so on, Sunday, then followed by the enumerated variables week_start, comma, week_end, followed by a semicolon. Here, the above two statements of definition of a enumerated data type and the declaration of the enumerated variables are combined together in one single statement. Now let us see what are storage classes. Variables in C can have not only data type but also storage class that provides information about their location, visibility, initial values, and lifespan. The storage class decides the portion of the program within which the variables are recognized. The first storage class is auto, meaning automatic. It is the default storage class. That means if we don't specify any storage class, then it is by default the auto storage class. The variables declared with auto storage class or without any storage class are the local variables known only to the function in which it is declared. So their visibility is local to the function in which it is declared. The initial values of such variables will be some garbage value, which means it can contain any random value, and the lifespan of such variable will be till the end of the function. Once the program control exits the function, then the lifespan of such variable is over. The next storage class is register. Variables with storage class register are local variables which are stored in the register, not in the RAM. A register is a type of memory inside the CPU which can be accessed faster than the normal memory RAM. The variables stored in the register can be accessed faster than those that are stored in the RAM. The initial values of variables of storage class register will be garbage, meaning it will contain any random value, and the lifespan of such variables will be till the end of function. Because register variables are also local variable, local only to the function in which they are declared. The next storage class is static. Variables of storage class static are also local variables which exist and retains its value even after the control is transferred to the calling function, which means if you want to retain the value of a variable even after the program control is transferred from a function to the calling function, then we declare such variables with the storage class static. The initial values of variables of storage class static are automatically assigned to 0 by the compiler, and the lifespan of such variables declared as storage class static is till the end of the program, not till the end of the function. The next storage class is extern. Variables of storage class extern are global variables known to all functions in the program. When extern is used with a variable, it is only declared, not defined. That is, memory is not allocated for that variable because it is defined elsewhere in some other file. However, if we define variables outside the main function without the use of the extern keyword, then those variables are by default global variables known to all functions in the program, and at the same time that declaration statement will also be the definition of the variables and memory will be allocated. The variables of storage class extern are given initial values of 0. The lifespan of such variables are till the end of the program. Now let's see some example of storage class declaration. The first declaration is auto int count. Here we are declaring the variable count to be of integer data type, and the storage class is auto, which means it is a local variable whose visibility extends within the function in which it is defined, and the variable count contains a garbage value, and the moment the program control is transferred from the function in which the variable count is declared to the calling function, then the variable count will lose the value it contains. The next declaration is register char ch. Here the variable ch is being declared as a character data type to be stored in the register memory, which can be accessed faster than the RAM memory. Now the variable ch is also a local variable whose visibility extends only within the function in which it is declared, and it will contain a garbage value as its initial value, and the variable ch will return whatever value stored in it till the end of the function. Once the program control is transferred from the function in which it is being declared to the calling function, then it will lose its value. The next declaration is static int x. Here we are declaring a variable x to be of integer data type, and its storage class is static, meaning the value of the x will be returned even after the program control has been transferred from the function in which the variable x has been defined to the calling function, and it will be returned till the end of the program, and the initial value of x will be assigned to 0 by the compiler automatically. The next declaration is extern long total. This statement declares the variable total to be of data type long integer and of storage class extern, meaning total is a global variable. This statement only declares the variable total, so this statement is not allocating any memory to the variable total because it has been already allocated some memory in some other file. The compiler will automatically initialize the value of this global variable total to 0, and the last span of this global variable total will be till the end of the program. Remember, auto and register storage class variables contain undefined values, that is garbage values, unless they are initialized explicitly, and static and extern storage class variables are automatically initialized to 0 by the compiler. We include the extern keyword explicitly when we want to declare global variable without defining them. Now let's see a small program in which various types of variables has been declared. To understand the concept of store class better, the variable m, which has been declared before the main function, is called a global variable. Here the extern keyword is implicit. When the extern keyword is implicit, the declaration int m defines the variable m to be of integer data type as well, and memory is allocated. If we had used the extern keyword explicitly, then the variable m will be declared only, not defined. This variable m, which is declared before the main function, can be used in all the functions in the program. It need not be declared in other functions because it is a global variable. It will contain the initial value 0 and it will return its value till the end of the function. The variables I and balance declared within the main function and I and sum declared within the function 1 are called local variables because they are declared inside a function. Local variables are visible and meaningful only inside the function in which they are declared. They are not known to other functions. For example, the variable balance declared inside the main function cannot be used within the function 1 without first declaring it, and the variable sum declared within the function 1 cannot be used within the main function without first declaring it. Note that the variable I has been declared in both the functions. Any change in the value of I in one function does not affect its value in the other. Now let's see the use of variable type qualifier const keyword. The value of a variable can be made to remain constant during the execution of a program by declaring the variable with the qualifier const at the time of initialization. For example, const in class underscore size equal to 40 followed by semicolon declares the variable class size to be of integer data type, and at the same time it is being assigned the value 40 to it, and this value cannot be changed by the program during the execution of the program. This statement tells the compiler that the value of the in variable class size must not be modified by the program. Next, let us see the use of the variable type qualifier volatile keyword. The qualifier volatile can be used to tell explicitly the compiler that a variable's value may be changed at any time by some external sources from outside the program. For example, the statement volatile int that declares the variable that to be of integer data type, and the variable that has been made volatile, which means the value of the variable that can be modified by some external sources outside the program, even if it does not appear on the left hand side of an assignment statement. When we declare a variable as volatile, the compiler will examine the value of the variable each time it is encountered to see whether any external alteration has changed the value. Note that the value of a variable declared as volatile can be modified by its own program as well. If we wish that the value must not be modified by the program while it may be altered by some external sources, then we declare the variable as both volatile and const as shown below. Volatile const int location equal to 100 followed by semicolon. This statement declares the variable location to be of integer data type, and it is being assigned the value of 100. Now this value of the variable location cannot be changed within the program because the variable location has been qualified by the variable type qualifier constant, but the value of the variable location can be changed by some external factor because the variable location has been qualified by the variable type qualifier volatile. So in one single declaration statement, we can use both the volatile keyword and const keyword to make the value of the variable constant within the execution of the program, but which may be modified by some external factor. That's all for now. Thank you everyone.